I wish you happy, healthy, long life. I want to tell you something before I start today's lecture. I know you have no classes, no school these days, and you do not have to go work either. At least most of you not working these days. So, if you have no special reason to go outside, stay home. And if you really want to go outside, once you come back, wash your hands. If possible, get a shower or body wash. That's the best. If you happen to have a lemon, clean your body parts specially exposed to outside with a piece of lemon. Okay, that again, you're not believing it just because I'm telling you. You remember the document I show you and gave to most of you guys in class. I show you this. You remember this? I believe you can see it. So again, if you have this, read this, live upon this. Alright, do not believe anything. I always asking you not to believe anything. You understand that, right? Okay, now if you have any questions on this or from the course material, feel free to email me. Now my Baruch email and personal email address as well, they both working fine, so email me. I got some emails from you guys. I answer to most of them, I believe. Some of them I did not answer yet. I might answer to them. Alright. Now besides that, I hope to do live session during class times. I'll let you know later. Question and answer session, and if you have any questions we can discuss, but I like if you email me those questions before that, so I can prepare some slides or whiteboard with answers. It will be quick then, right? So if you have any questions, email me, right? So let's go to today's lesson. All right. Now this stuff on whiteboards I prepare beforehand, so we can go through them pretty fast. At any time you can pause the video and go through them. Now today we're going to discuss section 2.3, limits and continuity. In this section, it is not hard, but it touches some subtle points. It's not just math, it has some subtle points, means delicate points that you need to understand, right? Now if it is not too small and not readable, I'm going to read everything here. You can take notes. Now this slide, it is just arithmetic that you know. Most of you guys know it, I believe. So just focus on that. Just I'm doing this part. This is not explained in the book. I'm doing this part because you have to have a knowledge on this part. Alright, here we discuss limits and continuity. Okay, now let's focus on the number line. This is the number line. Let us focus on approaching number 3. This number 3, I just grab a random number 3. Approaching number 3, I read from the beginning. Let us focus on approaching number 3 on number line from both sides. What is the closest real number to number 3 on its left hand side and right hand side? Now we want to find out the closest real number to 3 from left side and right side. Right? Now if you just write integers 0, 1, 2, 3, 4, you see the closest numbers to 3 is 2 and 4. But we're looking for the real number. We can subdivide this region between 2 and 3, 2.1, 2.3, blah blah blah, 2.9 and 3. So there we find on the other side also 3.1, 3.2. We'll discuss one side only so you can understand the other side. So in this side it is 2.9, other side 3.1. Now if you enlarge this region from 2.9 to 3.1, that's what I did in the next figure. 2.9 to 3.1, we can again subdivide this region from 2.9 to 3, 2.91, 2.92. Likewise we get 2.99 here. On the other side we get 3.01. Get it? Now we can enlarge this region between 2.99 and 3.01. We get this. Then we get the closest real number 2.999. On the other side 3.001. We can again enlarge this region. Likewise we can keep going this forever. This means what? I read this. This is an endless process. So you cannot say the closest number to 3 on either side. Therefore to implement this, we write this as limit x approaches to 3, which means getting closer to 3 but not equal to 3. We read this as limit x approaches to 3. Right? Limit x approaches to 3 means getting closer and closer. I showed you this is endless process. 2.9, 2.99, 2.999. Right? Likewise this is endless process, getting closer and closer to 3. So when we say limit x approaches to 3, what it means is we getting closer and closer to 3 but not 3. That's the thing you have to understand very clearly. Getting closer and closer to 3 from both sides but not 3. Now we want to specify in which direction we approach into 3. Now if you consider number 3, let me get a marker. To number 3, this side all numbers are smaller than 3. Right side all numbers are bigger than 3. So this side, left side to 3, we say negative side of 3. Relative to 3, this side is minus. Relative to 3, this side is positive, plus, right? So this region, this way we call 3 minus. We're using that. Let me read the next line. This here. To show x approaches to 3 from left hand side or negative side of 3, we write limit x approaches to 3 minus. You see this small negative sign on the top? This does not mean negative 3. This little negative sign on top of 3 means x approaches to 3 from negative side, means this way, negative side, or from left. 3 minus means what? Approaching to 3 from negative direction or left side. I often refer this as approaching to 3 from negative direction rather than saying from the left, right? Likewise, to show x approaches to 3 from right hand side or positive side of 3, we write limit x approaches to 3 plus. This little plus on top of that, or on top of 3, means x approaches to 3 from positive direction in this way, or from right side of 3, right? Alright, let's move to the next one. If you want to take notes, you can pause it and take notes, so you can go back always on the video. So I'm going to the next one. Now this gives you the big picture, right? This teaches you the big picture about limits. Now this thing I sketch, this everything together is the function fx. When we say fx, it is not just this piece or this piece or this piece. Fx consists of all these pieces, right? Now let's first understand the graph. Fx, in this side it keep going, that means it keep going like this. Come here, this is a sharp edge. At this point it is a sharp edge. You know what we mean sharp edge, we discussed this in class. After that it is increasing and it's going to infinity, and on the other side it's coming from infinity, go down. This place is smooth. This place is smooth. It is not a sharp edge, and increasing. And this is open circle. You know what it means? Open circle means it is not included. Again open circle, go down. This is an open circle, going up and going to infinity. And this time this is coming from negative infinity. Downside it is negative, coming from negative infinity. Stops here. This is a closed circle, and this is open circle. Again function increasing and going to infinity, right? So these are the things I want to pay attention. Limit x approaches to -2. fx approaches to infinity, x approaches to -2, why it is going to infinity? On both sides it is going to infinity. Right? If both sides is going to infinity, we say okay, f is as x approaches to -2, fx approaches to infinity. Let me see. Let's come back to this after we discuss the other one. I have this. This is good to understand this limit concept. We now use this limit concept on functions. Let's see if it focused well. Okay. Now this thing we learned, we now use this limit concept on functions. Remind that we can write a general point on a function fx as px comma fx. If this line is fx, if you know one point this is x, we x coordinate as x, we can write its y coordinate as f of x, right? So this coordinates of this point is x comma fx. Now this x gives us the position or x coordinate. This is x coordinate. Fx gives us value. It is the y coordinate. What you need to know is x coordinate is the position and y coordinate is the value. Right? Now this is the limit definition. It does not teach us any math. It teaches us notation, the limit notation. Limit. This is how you read this. Here I wrote it. The limit of fx as x approaches to a is L. Limit of fx as x approaches to a is equal to L. So when you have to remember, whenever you see limit of fx on one side, whenever you see this, we know this means the y coordinate or value, right? Therefore on the other side, this L again is a value, not a position. What this means, at the point x, value of fx, this whole thing means a value. So this means a value. On the other side, L should be that value. To find the limit, I'm reading this line. To find the limit value L, we have to find both left side limit and right side limit. You remember what left side limit and right side limit? The slide before I showed you, we get number 3, left side of 3 and right side of 3. So I should number this as second slide or second whiteboard. Okay, now to find the limit value, we have to find both left limit and right limit. Limit x approaches to a from negative direction is equal to L1, and limit of fx as x approaches to a from positive direction equal to L2. Right? To explain this concept, I take the left limit of fx as L1 and the right limit of fx as L2, right? Now just as 3 in the previous slide, I use A here. Now if when it's approaching to A from negative direction, it is L1, approaching to A from positive direction, it is L2. Now if these two limits approaching to A from negative direction and positive direction, if they are equal, and we can write this as just L, then we say the limit exists. If they are not equal, then we say limit does not exist. In short, we write DNE. This is it, DNE. Now there are two cases. If those two limits are equal, that is part A. Part B, they are not equal. If they are equal, limit exists. Now below I give you some examples. Now you see, now as x approaches to A from negative direction or positive direction, let me get a marker again. Negative direction, if it approaches to A from this way, what's the function value approaching to? This value, this is L. If x approaches to A from right side, still when it approaching to A from right side, we have to follow this region, this part, the top part. It is approaching to the same limit L, right? In this case, left limit equal to right limit, therefore we can say limit is approaches to L. Limit is approaches to L. You see, this point is open. That's exactly the thing you have to understand. When we talking about limit, the point FA, this circle point is FA. This does not matter. This is immaterial. In this case, it is open circle. That means FA does not exist. Still, limit exists. You see, if left limit equal to the right limit, the limit exists, but FA does not exist. Now here, this case is clear. Limit, the left limit and right limit both the same, and this is a closed circle that also included. So this is clear. Limit is L. Limit as x approaches to A, fx is L. This one. Now here, as x approaches to A from negative direction, what happened to fx? Fx is going to infinity, right? Now if you look at the right side, x approaches to A from positive direction, fx is again going to infinity. You see, in both sides, as x approaching to A from left side or right side, fx is going to infinity. So remember, it's the same thing. It's in both sides, it's going to positive infinity. Therefore, limit exists. Limit is infinity. Get it? In B, in case B, limit 1 does not equal to limit 2. Let's see what type of cases is that. Now we see this type of functions, what we call them piecewise function. In this region it behaves like one function. In this region, right side, it is behaves with a different equation. I shouldn't say function. It's the same function, In this region it's one equation, in this region it is different equation. Now if at A the left side is this, right side limit approaches to a different value. So this is your L1 and this is your L2. If you want, write here L1, here L2. So since L1 not equal to L2, the limit does not exist. Understand? If left limit not equal to the right limit, limit does not exist. Same thing here. Left side it is going to positive infinity, right side it's going to negative infinity. If they go into the same infinity, like this case, we say limit is infinity. But in this case, left limit is infinity, right limit is negative infinity. They are not the same. Therefore, we say limit does not exist. Right? Now, if you want to take a note on this, now you might have better understanding. We can discuss this. X approaches to -2, left limit going to infinity, right limit also going to infinity. Therefore, limit is positive infinity. F is, I note down those facts that you got to know. F is continuous but not differentiable at x equal to -4. At x equal to -4, function is continuous. You see, there is no hole here. It is continuous. But here it is not differentiable. On the last class, or in class I believe, we discussed this. At sharp edges or open places like this, discontinuities like this, function is not differentiable. At sharp edges again, at sharp edges, function is not differentiable. Therefore, at x equal to -4, it is not differentiable, but it is continuous. That's what it's saying. Now, f is not continuous and hence not differentiable at these points. X, all these are x values. X equal to -2. What are these points? Where function is not continuous. Just focus on not continuous. If it is not continuous, it is not differentiable. There is a theorem, we're going to discuss that. F is not continuous at -2. See, it's at both ends. It is going to infinity, but they going parallel to each other. They never connect each other. Therefore, function discontinue there. At 1, x equal 1, left end comes here, right end starts from here. There is a gap. What we call this? It is a jump discontinuity. X equals 2, x equals 2, open circle. It's again discontinuous. X equals 4. At 4, it's going to positive infinity, is then going to negative infinity. Therefore, at 4, it is not continuous. 5 again, it has a jump discontinuity. Function is not continuous. Wherever function is not continuous, function is not differentiable, but not vice versa. If the function is not differentiable, does not mean it is not continuous. For best example is this point. Sharp edge, function is not differentiable, but it is continuous, right? So what we learn here, if function is differentiable? Definitely it is continuous. If the function is continuous, that does not mean function is differentiable. It may be differentiable, maybe not. As I said, we're gonna learn that as a theorem later on, right? Okay, next one. Okay, on the right side, this is my Baruch email address. If you still, for those who still do not have my email, I believe now everybody get my email address, but still I'm putting it here in case you can copy this down. This is Baruch email address, or this is my personal email address, right? So if you have any question, you may send to one of them. Try Baruch email address, or you may email to both of them. Alright. Frequently I check Baruch email address, so Baruch students, please send email to Baruch or both. Alright, now let's do an example. Now you have good understanding with my previous slide about continuity. This is an example. Now when the function appears in the form of an equation, now we want the question appear just like this: find limit of 2x plus 4 as x approaches to 3. What we want to find, we want to find the limit as x approaches to 3. What happened to 2x plus 4? As we discussed, to find that, what we need to find? We have to find the left limit and right limit. Now in class we did some examples like this. There you may remember, I said if you substitute and if it gives us a sensible value, the limit is just that. That is true. Now let's see. Now here what we learned just before, the limit to be exist, the left limit should equal to right limit. Now we already know the answer to this question. When x is approaching to 3, 3 times 2 is 6, 6 plus 4 is 10. That's the answer. Now assume we don't know that. We going to try what we learned just before. Now what we do is we write few numbers left side of 3 and right side of 3. Just before 3, 2.999. Before that 2.998. Before that 2.997. Right side of 3, 3.001. 3.002. Likewise. Now these are the function value. Substitute this x value in the function, means for x. We take this part as fx. So this is our fx. When we substitute this x value for wherever you see x, we get the function value. Now you may have a question why I do this 2.999, not 2.9. Yes, if you write 2.9, 2.8, 2.7, that's fine, right? on the right side too, but to get more accurate answer, we should get more decimal points, right? So here I pick 2.999, 2.998. Now corresponding fx values, you know fx is same as y values, they are 9.998, 9.996, 9.994. Now if you look at carefully the y value, when we approach into 10 from negative direction, those numbers on top are the left side. These are the x values. Now let me find the red marker. This side is the negative side of 3. What is this side? This is the positive side of 3. Think about the number line. 2.99, 2.998. These points are further away from 3 to the left. These numbers are going to the right. Right now, when we coming towards 3 from left side, you see y value is getting closer to what? 9.99, 9.996, 9.998. It is getting 4, 6, 8, getting closer and closer to 10. We don't know this value, so that's why I put this in red. You may not write this number here, but look at the right side. We, in the same way, we get numbers for 3.001, 2, 3. Now we approach into 3 from right side. That means we come in this direction. I draw an arrow here. We come like this, coming from left, coming from right. What happened to the y value? Y value is 10.006, 10.004, 10.002. It is decreasing, you see. It is getting closer and closer to 10. Therefore, we can assume it is, see, this is increasing and this is decreasing. Therefore, we can assume the limit approaches to number 10, right? Again, you may substitute it, and if it gives you a sensible number, that's the limit, right? But later on, we're gonna do an example which is not giving us a sensible number, right? Now, okay, let's go to the next slide. Okay, this is another example. Find what happened to this function x square minus 9 divided by x minus 3 as x approaches to 3. Let's do the same thing. Don't look at these things in red. Let's do this. Let fx equal to whatever the expression given here. Fx equal to this expression given here, x square minus 9 divided by x minus 3. What we do the same thing. We want to find what happened to fx as x approaches to 3. Therefore, we select few numbers to the left of 3 We start from here. We start from number 3. We write few numbers next to 3. You may write 3 decimal points, you may write 4 decimal points. Doesn't matter. More decimal points, better it is. Now this looks the same as previous example. In this way it is from the left. This side is the positive side of 3. This is the negative side of 3, and this is the positive side of 3. Now in this case, let's see where it is approaching. When x approaches to 3 from negative direction, what happened to fx? Look at these numbers coming from this direction: 5.997, 5.998, 5.999. Right? On the other hand, when x approaches to 3 from positive direction, 3.00321, what happened to y value? 6.003, 6.002, 6.001. So we can assume it's approaching to what? It's approaching to 5. See, this is increasing, this is decreasing. So we can assume it is approaching to limit of 6. But if you directly substitute 3 here, 3 square is 9, 9 minus 9 is 0, 3 here, 3 minus 3 also 0, you get 0 over 0, which is undefined. At 3 it is undefined. Now here's the place where the definition comes. The left limit is getting closer and closer to the right limit, 5.999. Now if you calculate the y value for 2.9999, means with extra decimal point, these 2 points will be even closer, right? Therefore we can say it has a limit, it's approaching to a limit of 6. This side keep decreasing, this side this side get increasing, this side is decreasing. Therefore it's approaching to limit 6. So we can say the answer to this is equal to 6, looking at this, right? Now it is not by direct substitution. If you do direct substitution, you get undefined at 3. Now in fact we did this type of example in class. Now look at the right side in red. What if we do this in this way? Limit, what we want to find is limit of x square minus 9 divided by x minus 3 as x approaches to 3. We see we can factor the top. So we factor, then x minus 2, x minus 3, x minus 3 to x minus 3 cancels out. We get only x plus 3. Now if you substitute 3 here, 3 plus 3 is 6, right? Is that good? The problem is this: when we cancelling out, we assume we divide this by we assume x is not equal to 3. We want to find out what happened when x approaches to 3. When we cancel out this to this, we assume what we doing when we cancelling out. What cancelling out means, we divide by x minus 3 and x minus 3, top and the bottom. We divide by x minus 3. When we divide by x minus 3, we assume x minus 3, we assume x minus 3 I write it here, minus 3 not equal to 0, and this means we assume x not equal to 3 if you bring this 3 to the other side, right? Can we assume this x minus 3 not equal to 0 or x not equal to 3? We cannot assume that because we don't know, right? Now therefore we shouldn't do it. But since we need only left limit and right limit, means we do not want the value at 3, so we may assume we want to get the value when it is closer and closer to 3 but not 3. Understand? Therefore it is not that unreasonable we assume x is not equal to 3, right? Then we can cross out this to this and we can get 6. Therefore this is an alternate method which is much simpler than writing all these numbers, but this method is very important. These are algebraic techniques, right? We factor this. We learned few algebraic techniques. If you have radical, we do something else. There is a problem, I'll let you do it at home. Now if we can use algebraic techniques, first we can do it with that. If we cannot use algebraic techniques, then the only way is this, using a table. Now I'm gonna show you an example where I show you. Now let's see if we can do this using any algebraic techniques. Determine the limit of 3 to the power x minus 1 divided by x as x approaches to 0. Limit of 3 to the x minus 1 divided by x as x approaches to 0. Direct substitution. By direct substitution we get this. 3 to the 0 is 1. Anything to the power 0 is 1. 1 minus 1 is 0 divided by 0. 0 divided by 0, undefined. Now we may wonder if we can do this with any algebraic trick, algebraic technique. Can we use any of them? Factoring, what else? Remember, multiply by conjugate, that doesn't help. If you may try, right? So in this case no algebraic tricks or techniques are applicable. Therefore in such a case table works. Table works with anything, right? So we can I write the same similar table like we did before. We want to find what happened to this, therefore we take this as the function, let fx equal to this part, and we create the table. Remember, we start creating table from 0 because we want to find what's happening when x is 0. Then we write both sides. In this case we write 4 numbers because the accuracy, you do not see these numbers changing if you use 2 decimal places or 3 decimal places, right? When you, this is what it is. Now you may wondering, should I use 1 decimal place, 2 decimal place, or 3 decimal places? First try 1 or 2 decimal place and write the second number. When you write the second number, check your answer for fx. If it is the same, go to the third decimal point and try. So when you get third decimal point, still you don't see any change. You see, 8 and 8. If you get 2 decimal points here, you get 9 and 9, 8 and 8. Now if you get 4 decimal points, then only you see a change, 6 and 5. Right? We want to see a difference between these y values. So I use 4 decimal points, negative 0.0001, 0.0002, likewise. So I calculate fx values. How we do it? We substitute these x values here. No need to tell you, now you know how to calculate that, and we can make this table on the right side too. After we creating, then we see carefully. Now we know this is the negative direction of 0 and this is the positive direction of 0. When you come to 0 from negative direction, what happened to fx? See, these decimal places are the same. The only place changing is the last decimal point, 4, 4, 5, 6. So we can assume it is increasing. Now here, look what happened. 9, same decimal point, 0, 9, 8, same thing with all 3 values. Last decimal point is changing, 8, 7, still it is 7. We can assume it is decreasing. You may write the next point 2. You will see it is decreasing, but to what value it is decreasing? 1.0986, 1.0987. So in this case, we may wonder where it is approaching, 1.0987 or 86 or something in between. In fact, it should be somewhere in between, but we don't know. In this case, both answers are acceptable, right? Understood? You may write 1.0986. That's what I explained here. Now, for such limits where we get 0 over 0, something like this, undefined answers, we have another rule. We didn't do it yet. It is on section 2.12. I write it here. There we use a rule called L'Hopital rule. This sometimes called L'Hopital rule or sometimes L'Hopital rule. It's on section 2.12. Don't worry about that right now. So if you do the table and it is getting closer and closer to a number, you get the point. It should be getting, now on this side it is increasing and this side it is decreasing towards a single number, right? Now this is the point. This is decreasing and this also decreasing. We cannot say that, right? We should see it is getting closer and closer. These numbers getting closer and closer means when you look at these y coordinates in this direction, the left side numbers and right side numbers should getting closer and closer. Then we say limit exists. In this case we can say either this number or this number, or up to 3 decimal points. We can say, for the safe side, we can say limit is 1.098. or 1.099 approximate to 3 decimal places. Alright, okay. Now after that, let's go to the book. We on section 2.3. If you go to page 208, there are some theorems. I wrote that again on the whiteboard. I'll show you it right now. If it is focused. Alright. Now again, there are few theorems about limit. I get this from the book. The page number is again page 208. Let's see what these theorems means. If limit x approaches to a, fx is equal to L, and this is how we read it. Limit of fx as x approaches to a is L, and limit of gx as x approaches to a is m. So there it is clear to you, we're talking about two functions, f and g. As x approaches to a, fx approaches to L and gx approaches to m. So theorem 1 says limit as x approaches to a, c equal to c. What is this c? Hold on, let me get a marker. This c is a constant. C is a constant. So if it is a constant function, for instance, say fx equal to fx equal to 6, fx equal to 6. So what fx equal to 6 looks like? This is like y equal to 6. Y equal to 6 is a horizontal line. Remember, y equal to 6 is a horizontal line. Regardless of the x value, y value never change. Since it is a horizontal value, its y value is always 6. Therefore, limit of constant function is the same thing. This is an example, fx equals 6. Now, limit of x as x approaches to a. Now here I said if direct substitution gives us a sensible answer, do that. When x approaches to a, if you substitute a here, we get a. Therefore limit is a. Limit of kfx as x approaches to a, where this means, this semicolon means where k is a constant, this is equal to k limit x approaches to a of fx. Now limit of fx as x approaches to a, we take that as L, therefore this is k times L. Limit as x approaches to a, fx plus or minus gx. This is for plus and minus as well. Let me change this minus to red. Minus to red. Idea is this plus on left side go with all these pluses, and minus on red go with this red sign minus, right? That means limit of sums we can write as sum of two limits, right? This is L and this is M. Now limit of product we can write as product of limits, product between these two. So we know this is L and this is M, therefore it is L times M. Limit of a quotient fx divided by gx, this is a quotient, is same as quotient of between two limits of fx and gx. This is L and this is M, therefore this is equal to L over M. For any real number n, limit of fx to the power n as x approaches to a, we can write as, we can again move this limit inside, we can take the limit and raise it to the power n. Now we know this part is, what is this part? Limit of fx as x approaches to a, L, therefore this is L to the power n, right? This again in the from the book, but to continue your notes, I suggest you write this stuff, pause the video and take notes. Alright, now what else? Alright, so I'm gonna erase this. Now let's do a piecewise function. This is from page 210. Fx equal to negative 2x plus 6 if x less than 1, x plus 1 if x greater than or equal to 1. given this, we have to determine limit as x approaches to 1 fx. Understand the question. This is example 5. Given this, fx is defined as negative 2x plus 6 if x is less than 1. If x is greater than or equal to 1, it is 3x plus 1. Now we want to find out the left and right side limits as x approaches to 1. Now this one, it has a negative slope and positive y-intercept. So it's going like this. This one, it has a positive slope and positive y-intercept. Now this is the question. Now it is our job to find if this second function, we know it is increasing function, it is just like this, but we have to find out if it goes like this or goes like this or goes like this. Understand? Now how we determine that? I take off all these 3 and negative, this is negative 2x plus 6. Now let's find out this x, when x is less than 1, this point is 1 on x-axis, x-axis, y-axis. When x equal to 1, this is not applicable. This is only when x is less than 1. Therefore this should be open or close. This should be a closed circle, open circle. This point should not include. Now when x is equal to 1, it should behave like this. Before we get into this, let's find out when x is 1, what happened to that. From that we can find out when x is getting closer and closer to 1, where this fx value is getting closer to, means corresponding y value. If you substitute 1 here, 2 times 1 is negative 2 plus 6 is 4. It is getting closer to 4, but we should not include that point 4, open circle. Now when x is equal to 4, 4 times 3 is 5. 4 times 3 is, when x equal to 1, 1 times 3 is 4, 4 plus 1 is 5. Wait, we did a mistake, I think. When x is 1, negative 2, 6 minus 2 is 4. That's good. Let me see the book again. (3x plus 1). Right, it's good. When x is 1, 3 times 1 is 3. 3 plus 1 is 4. This function starts from this point. You see, when x is 1, 3 times 1 is 3. 3 plus 1 is 4. I do it in a different color. find a different color. This part I do in red, so it starts from the same point, and I shade this to indicate this is included. It has a positive slope and positive y-intercept. It should go like this. Get it? Now looking at this, what can we say? As x approaches to 1, now what is fx? Fx is it blue one or red one? Fx is both. I write fx. Fx means both together, because fx defined as a piecewise function. This like this, less than 1, like this when x is greater than or equal to 1. So when it is getting closer to 1, the left limit is getting closer and closer to 4. The right limit, when we say right limit, we have to follow this red line. It is getting closer and closer to the same number 4. Therefore limit exists. Therefore we say limit as x approaches to 1, limit of fx as x approaches to 1 is equal to 4. Right? Alright, let's do another example. Another piecewise function. Negative 2x plus 6. X plus 4. This is example 6 in the book. Now you have the picture in mind, I believe. Negative 2x plus 6. What's important is this. Negative 2x plus 6. I do this in blue color. Negative slope and positive y-intercept. Negative slope, it's going like this. We want to find out what's happening at 2. X is less than 2, that means not equal to open circle. Positive slope and positive y-intercept. Now before we do the line, as I said, we want to find out if it is a line like this, or a line like this. So before we do that, we substitute this number and check what is the y value. Now if you substitute it here, 2 times negative 2 is negative 4. Negative 4 plus 6 is positive 2. Now if you substitute 2 here, 3 times 2 is 6. 6 plus 4 is 10. That means it is somewhere up here. From there it has equal sign, therefore we shade this circle, and it has a positive slope and positive y-intercept. It should be go like this. Let me use different color. It should go like this. Right, now here you can learn something. Limit when x less than 2, the left limit. How now you going to learn how to write this left limit and right limit. Limit x approaches to 2 from negative direction. Negative direction means this. Relative to 2, the negative direction is this. This is negative. Wait, I could have do it in blue. This is the negative direction of 2, and this is the positive direction of 2, where we follow the red line. Now limit of fx as x approaches to 2 from negative direction, so I write 2 minus here. Equal to which part we should follow? 2 from negative direction, we have to follow this part, which is negative 2x plus 6. So I have to substitute 2 in this first equation. Negative 2 times 2 plus 6. This is negative 4 plus 6, which is 2. The other part I write in red for you to follow easily. Limit x approaches to 2 from positive direction. You see, it's little plus positive direction. Fx, which part we have to follow? This one, which is this. We have to substitute 2 here, equal to 3 times 2 plus 4. 3 times 2 is 6. 6 plus 4 is 10, which is 10. X-axis and y-axis. Alright, now look, now these two limits are different. Therefore, next line you write therefore limit x approaches to 2 from negative direction, fx does not equal to limit x approaches to 2 from positive direction fx. Two sides are not equal, therefore limit x approaches to 2, no positive, no negative. Since these two limits not equal, this limit fx, what do you think? Since they're not equal, it does not exist. TNE means does not exist. Alright, that's it. This is the answer. Limit does not exist in this case. Okay, I'm going to erase this. In the same way, I want you to do examples 8 and 9. Page 214. Page 214 and page 215. Right, try that. If you have any question, let me know, email me, we can discuss during the class session. this is the theorem I told you before. At any point in its domain at which a function is differentiable, it is not continuous, right? I already showed you an example. At a sharp edge, at sharp edges we learned function is not differentiable. When we learned differentiation in class, you maybe remember using the definition of differentiation, using the limit as it approaches to 0, fx plus h minus fx divided by h. Remember, there we saw at sharp edges function is not differentiable. Therefore, at this place function is not differentiable. Not differentiable. But at this place point function is continuous, right? Anywhere beside that, anywhere, if the function is differentiable, it is continuous, right? If it is not continuous, definitely it is not differentiable. But if it is continuous, you cannot say function is differentiable. Therefore, I add this part here. I write in red, not vice versa. Which means if function is differentiable, it is continuous, but if it is continuous, you cannot say differentiable. It may differentiable, may be not differentiable. For instance, at a point like this, it is continuous and differentiable. At this point, it is continuous but not differentiable. Clear? Now let's do another question. fx is defined by this: fx equal to 3x to the power 4 plus 2x cubed minus 3x plus 6. We want to prove fx is continuous everywhere. Now, what is this one? This is a polynomial, right? Now, if it is continuous everywhere, according to the theorem that we learned just before, if we could show that its derivative is continuous, derivative exists at any point, then the function is continuous everywhere, right? Let's find the derivative of this. So this is a good example for you to remind what we learned last time, how we find the derivative. df dx, in our short notation it is f dash x equal to, you remember, x to the power n. When we differentiate, nx n minus 1, this is 3 times 3 is a constant. We differentiate this one with respect to x. 4 x to the power n minus 1 is 4 minus 1 is 3 plus 2 times 3x to the power 2 this one minus 3, isn't it? 3x means 3x to the power 1. 1 x to the power 1 minus 1 is 0. Anything to the power 0 is 1. So this times 1, 3 times 1, which is 3, right? Plus constant term, derivative of constant, any constant is 0, right? So we get f dash x equal to 12x cubed plus 6x square minus 3. This is a polynomial. This is what? This is a polynomial. Any polynomial any polynomial is defined any polynomial is defined for all real numbers. Real numbers, for all real numbers we use this notation. I put it in parentheses. That means it's, the derivative of fx is defined for all real numbers, which means f is differentiable at any point. This means differentiable at all points on real number line. This means real number line. If any function is differentiable at any point, that function is continuous. This we proved that f is differentiable at any point on the real number line, therefore fx is continuous everywhere. Therefore f is continuous everywhere. Get it? I'm erasing this. Another example number 12. This is example 12 on page 217. Example 12 on page 217, fx equal to x minus 3 divided by x square minus 3x. Okay. In part A, at what points f is discontinuous? Now, first of all, let's factor this out and simplify. This is equal to x minus 3 divided by x times x minus 3. Right? Now be careful, the question is not to simplify. If we cross out these x minus 3's, then we get this is equal to 1 over x. To do this, what we assume, we make an assumption in doing this. X minus 3 not equal to 0. If this is 0, you cannot divide by 0. Right? If we assume this, this means we assume x not equal to 3. Now question is asking at what point f is discontinuous. Function is discontinuous, we know wherever the denominator 0, function is discontinuous. Therefore we can say function discontinuous for part A. When denominator is 0, x times x minus 3 equal to 0, we get x equal to 0 and x minus 3 equal to 0. That means x equal to positive 3. At x equal to 0 and x equal to 3, the function is discontinuous. Part B. One out of these 2 points, one point is a removable discontinuity. How would you define why that point so as to remove the discontinuity? When x equal to 0, no matter what, this is undefined or going to infinity. But when x equal to 3, we get 0 over 0. Now if you cancel out this, we get 1 over x. There we assume x not equal to 3, right? Now let me erase this. This is part A. If x not equal to 3, we get fx equal to 1 over x. But the problem is when x equal to 3, it is discontinuous. To avoid that discontinuity, we have to define a value. When x equal to 3, without this part, what should be the y value? When x equal to 3, we get f3 equal to 1/3. Right? Now, therefore, if we define f3 equal to 1/3, the function is continuous at x equal to 3, right? Therefore, we say x is continuous, f is continuous at x equals 3. So how you define the y value? We define f3 equal to 1/3 so that at x equal to 3 it is continuous. On the other hand, when x equal to 0, it is not a removable discontinuity. In part C, at what point does f not have derivative? When it is not continuous, it has no derivative. At what point does f not have derivative? We already saw the derivative means function is not continuous at x equal to 0 and x equal to 3. Okay, you get this? So this is the answer for part B. Right. I'm gonna erase this part B. Part C. At what point does f have f not have a derivative? F is not continuous at x equal to 0 and x equal to positive 3. If x equal to 0, denominator is 0, so this is infinity. When x equal to 3, 3 minus 3 again 0, denominator 0, same story, right? We know from the theorem, if it is not continuous, it is not differentiable. Therefore, f is f has no derivative x equal to 0 and x equal to 3. Since f is not continuous at x equal to 0 and x equal to 3, f has no derivative at x equal to 0 and x equal to 3. Part D. If you redefine f so as to remove the removable discontinuity, is the function differentiable there? Get this part? Now, part D. Now, the question is this, part D. If you redefine f so as to remove the removable discontinuity, that means we define f3 equals to 1/3. It remove the, when f3 we define like this, we can remove the discontinuity, but still at 3 it is not differentiable, because as it is getting closer to 3, we have to see the behavior of this. You will see that with some of the other examples we can remove the discontinuity, but at that point it may not be differentiable. Okay, so the answer is no. Okay, what else? That's 12. Let's do another example. Example 13. Given determine Okay. Given fx comma y equal to 2x square y cube, determine limit fx plus h comma y minus fxy divided by h. So by the way, what is this ratio? That's the derivative of f. It is not as in this question. This is the derivative of f with respect to x. This is same as this part not asking in the question. This is df over dx. If we change y, which is the part b, that is df over dy. So this part is additional. It's not asking this question. Now let's do this one. X is changed to x plus h. Therefore all you have to do is change this x to x plus h. This is same as, I start somewhere here, limit as h approaches to 0. I'm gonna write this fx plus h. I write it in different color. Don't need this, I erase it. Two times x plus h square y cube. I don't change y. Why? Because y stays the same. X change to x plus h. Y stays the same. Change x to x plus h. Keep the y. Right? Minus fxy. Fxy is same as given thing. 2x square y cube. Divided by h. Two times x plus h square is what? X square plus 2hx plus h square y cube minus 2x square y cube divided by h. Limit as h approaches to 0. Distribute, you have to multiply everything inside with 2y cube, then 2x square y cube plus 2 times 2 is 4 4h x y cube. This one 2 times h square is 2h square y cube. We multiply everything. Now this part minus 2x square y cube divided by h. Now simplify, cross out like terms. 2x square y cube, negative 2x square y cube, cancel them out. Now here limit as h approaches to 0. Now from these two terms, you see h is a common term. We can take out h times Also we can take out, oh no, just take out h, 4x y cube minus 2h y cube divided by h. Sorry, I like this h small. Divided by h. Okay, now this h to h cancels out. Now we can substitute h. Now what's in the denominator? 1. H times 1, h times 1. When we substitute 0 for h here, we get 4x y cube minus h is 0, therefore this part is 0, therefore minus 0 is equal to 4x y cube. Is that clear to you? Or x y cube. Okay, that's the answer. Right. Take this. I'm gonna erase this. I let you do part B in the same way by yourself. Part B is this. Determine this is part B. Limit as k approaches to 0 divided by k. Right, I'm going to erase this part. Now as before, if you just read the y part, this is like fy plus k minus fy divided by k as k approaches to 0. Then what is it? This the derivative. This actually we call partial derivative, because we have function with two variables x and y. We differentiate this with respect to one of the variables. Before we differentiated that with respect to x. Now we differentiating the same function with respect to y, which means this is equal to df over dy. Right. I'm gonna substitute that and I'll let you do the simplification. This is equal to limit as k approaches to 0 to get fx y plus k. See the difference, x stays the same, y change to y plus k. Therefore on the right side what we should do, wherever you see y, change that to y plus k. Don't change anything with x. Right, then we get 2 x square y change to y plus k to the power 3 minus fx comma y is the given thing, same thing, 2x square y cube divided by k. Since this is not part of the question, I take this off. I just wrote it for your knowledge. Now we have y plus k cube. Before we did y plus k, x plus h square. There we have formula. For this we do not have formula. What we can do is, what you can do is, either you can write this as like, okay, y plus k cube is same as y plus k square times y plus k. Right? First distribute this, then multiply that with this. Right? You know how to distribute this. This is y square plus 2yk plus k square. Then distribute it with this. You get longer expression than we did before, but it is doable. Again, do it and you should get the answer. I give you the book answer, 6x square y square. Alright, so this is the answer. This is this part. When you distribute, you get this, distribute and multiply by this. So complete that question, do your homework. Again, if you have any questions, send me an email. Again, for those who I did not respond, I'm going to respond that, and you may use either email, but send an email definitely to my Baruch email. I check that frequently. Alright, so stay safe guys. Thanks.